Wolfson, who's going to tell us about essential dimension via prismatic cohomology.
Thank you so much for having me. Hold on, I'm trying to figure out how to get these screened. There we go. Okay, great. So it's a pleasure to be here virtually to speak in the seminar. And I was really delighted when Ryan invited me. It's sort of very nice to be back. I think I was last in the seminar 5 years ago. Craig, correct me on that, but it's been some time. And a bunch of stuff has happened between then and now. So it's nice to be back. So I'm going to be giving a talk. I think of myself as a topologist. This is a talk that's sort of aimed at a topological audience that's been expanding in sort of interests with a lot of kind of influence from number theory and algebraic geometry in recent years. And you can sort of understand this talk as like of a piece with that kind of thematic. So this is the title, and I'll say this talk in some ways it's both a talk about some things that we were able to do, and as you can see in this photo from I think 2019, there's some sort of expectations, some range of expectations in the collaboration about just how far we'd be able to push this, and I'll be telling you sort of how that played out in the intervening years. So this is Mark Kissen on the left and Benson Farb in the center. Are my co-authors on this paper and sort of the broader project that this is coming out of. And the kind of basic setup that I'm going to be talking about today, I'm going to consider kind of branch covers of complex varieties. So if you want to ignore the branching entirely and just think this is like a good old-fashioned covering space in the sense that we teach in first-year topology, that's totally great. If you want to hold your favorite example in your mind, the branch cover of P1 over itself by Z goes to Z to D is not a bad one, though most of this talk will be particularly trivial for that one. But that's sort of a good example. One question that you can sort of ask, and this is a flavor of question that's been asked for about 100 years now, and in some sense goes back much further. You can ask sort of how complicated is this branch cover? And one kind of measure of complexity is, did it really come from something? Does it intrinsically need all the dimensions of the base space in order to sort of talk about the branching that's happening? Or could you compress it to something of lower dimensional? So while, you might have a branch cover of, a billion dimensional variety over a billion dimensional variety, maybe secretly after some change in coordinates, it comes from a curve, right? That kind of thing. And we sort of formalize this by saying, our cover is compressible if there exists a branch cover of lower dimension, a dense risky open of the base space of our original thing, a map from that open to the base of our other branch cover, and an isomorphism of after pulling back with the Z-twiddle and the sort of dense open piece of our total space, right? So maybe after kind of throwing out some bad locus, we find out that we can secretly recover our original branch cover as a pullback of something of much smaller dimension. And if so, we say that it's compressible, and all the data here is a compression. All right. And a related concept which has received a lot of interest and where you can really say quite a bit in recent years is this notion of P compressibility. So the difference between compressibility and P compressibility, you've got this prime number P, and instead of a rational map from the base X to Z, you allow a rational correspondence of degree prime to P. So that is essentially like a auxiliary branch cover, say, C over U. We require that the degree of that thing is not divisible by P. And then after restricting everything along that auxiliary branch cover, we have our compression. All right. And the sort of basic theorem I'm going to sort of organize the talk around it comes out of this paper of the same title. And the statement is if you have a complex abelian variety, then for all but finite many primes, the P isogeny cover. So you just take your abelian variety A, and you send each point in A to the Pth multiple of itself. This cover is P incompressible. right? So somehow like abelian varieties, like the arithmetic of say p torsion points in abelian varieties is of maximal complexity by this measure for all the finite remaining primes P. All right. And this answers almost all of a conjecture of Patrick Brosnan. Patrick conjectured that this is true for all complex abelian varieties and all primes. So you have some question about some sort of bad cases. And the reason I'm sort of telling you about this in topology seminar is that our obstruction, our witness to this complexity is going to be good old-fashioned characteristic classes in the like Milner-Stasheff type sense of them, or more generally like for a finite group G, cohomology of BG will give us the obstruction. And I'm stating this for abelian varieties, for sort of complex tori have an algebraic structure on them, because these are both very simple topologically, but very rich algebraically. And so they kind of give a nice class of examples to see this interplay of topology and arithmetic here. But the method applies a lot more widely. So a closely related class of examples is if you look at a product of Riemann surfaces or of complex curves, you can look at the mod P homology cover of that product. So the finite cover corresponding to the subgroup of pi 1 that vanished, that's the kernel from the map from pi 1 onto mod P homology. Again, those will be P incompressible for almost all primes also. That extends work of Gaber for elliptic curves, for complex one-dimensional tori. And then there's a rich class of examples that show up if you start thinking about things like arithmetic lattices in algebraic groups. You get these very rich objects called locally symmetric varieties, and these objects come endowed with these very rich sort of systems of finite covers. So if you're sort of saying, okay, what is a great source in nature of examples of like interesting finite covers in interesting spaces, this is one of the first ones I'd sort of point you to. And we're able to kind of give new examples where these covers are sort of are not P compressible. So they're sort of maximum complexity by this measure using characteristic classes. So that's a new case of the conjecture due to Patrick Brosnan and Najmuddin Fakhruddin. Great. So I sort of started off and I sort of stated a problem and introduced some examples. And then I'm going to kind of spend the rest of the talk kind of giving some context for this theorem. And I guess as a kind of advertisement for how this talk is going to be organized, this is a picture from a talk that Arnold gave and I guess wrote towards the end of his life. And it's a kind of amazing article. It's called From Superpositions to Dynamical Systems, Hilbert's 13th Problem, something, something, something. And right off on like the first page, Arnold sort of, gives some introductory remarks. Then he has this picture and the text is like, it, proceeds that in his view, mathematics is like a mushroom. And in this kind of analogy, the fruiting bodies, the actual like mushrooms that like we see above the surface, those are the theorems. But in Arnold's telling, most of the organism, most of the mushroom, most of the mycelium exists below the surface of the soil. Outside of view, there's huge complex things going on there that we are, only barely beginning to be aware of as a society. And most of it is just sort of not something that's accessible to us. And in sort of order of sort of greater structural importance and greater inaccessibility, or however you want to read this drawing, Arnold said, theorems are the little tiny things that the organism puts off from time to time to propagate itself. But the actual organism itself consists of problems, conjectures, mistakes, and ideas. And so I figured that will give the outline of my talk in what follows. I started with the theorem, and then we'll go through the problems, conjectures, mistakes, and ideas, and sort of work our way through this piece of the mathematical mushroom. Any questions or anything on any of the objects or the notions I introduced or the theorem that I stated before I keep moving? All right, I'll proceed. And just like interrupt me, and I think you should just be able to interrupt me if you have any questions. I can't, like the camera is sort of pointed at the door right now, so I can't quite see if anybody has a hand raised, but just like call out and or wave your hand and get the camera to point at you. And I'm happy to be interrupted. All right, so let me talk about problems. So this notion of kind of how complicated is a branch cover, or really this now encompasses a finite group, or more generally an algebraic group, or a split functor in Reichstein's sense, or a variation of Hodge structure, or an enumerative problem, or an arithmetic lattice. Like there's a whole bunch of classes of objects that like show up in algebraic geometry and in the sort of topology that shows up there. And you can ask in all of those, like how complicated is, the given object. And that's sort of what I want to kind of advertise under this sort of heading of resolving problems. And this language is very classical. It comes to me via Klein and Hilbert and Chebatarov in the sort of the early 20th century, late 19th century. And in some sense, the questions we're asking go back a long, long ways in math. And, a basic one is like, how complex is a polynomial? Or put another way, how complicated is the formula that solves a given class of polynomials? That's essentially the same question in algebraic guise as how complicated is a branch cover. An enumerative problem, these are all sort of similar. An algebraic group. Power series, this shifts it into a question of analysis. And this shift, I think, was first put in the literature by Enriquez and then Hilbert shortly thereafter. You can start kind of playing with this in variation of Hodge structure and arithmetic lattice. So this is a kind of a set of questions or a game that you can play. How complicated is some given class mathematical objects? And does it have some like minimal intrinsic complexity that accounts for certain things that we can or can't do about it? And the basic idea in this sort of whole paradigm, this idea, maybe the first point you can locate it in literature is in the work of Schernhaus in the 1600s, is that, well, like multivariable calculus is harder than single variable calculus, right? I think that's an experience that most of our students know. And sort of somehow like the complexity that we're measuring is the number of variables that are needed to build a gadget, right? How many free parameters do you need in order to construct something? That's sort of the intrinsic complexity. And there are other notions of complexity, right? This is not like a computational complexity where there you care about like what's the minimal number of steps that you need to do to perform an operation. And here it's like, well, maybe I need to do an awful lot of arithmetic, but if I allow myself an unbounded amount of arithmetic, I only need one variable functions, right? It's sort of orthogonal to that. But it's a nice notion. It's one that has been around for centuries. And you can think about this geometrically as like, what's the dimension? And so this sort of motivates or connects to this notion of compressibility that I was asking earlier. This idea kind of gets defined in the sense that I'm sort of talking about in this talk, comes out of work of Kronecker in the 1860s, and then Chebatarov in his 1932 ICM sort of devotes about a third of his talk on problems in modern Galois theory to this. And then again, it kind of lays dormant because, a bunch of things happen in the world between 1930 and say 1950. And so it lies, this is sort of forgotten. And then in the late 90s, Joe Buehler and Zinobi Reichstein kind of rediscovered it and reinvented it. And we've had a kind of, it's grown into sort of a minor subfield in the last 25 years. And the sort of measure of complexity is called essential dimension. That's Buehler and Reichstein's term. And it says that if you have some branched cover, then its essential dimension is the least d, such there exists a compression of that branch cover onto something d-dimensional. Right. Chebatarov had called this the true transcendence degree, and he was thinking in terms of field theory. I like geometry and topology, so I'll think in terms of varieties or birational geometry, and sort of follow and adopt Buehler and Reichstein's language. All right. And then one of the things that happened that's genuinely new in the kind of the contemporary moment is they started playing with this notion and realized that this essential p dimension, where you don't just allow compressions, but you allow P compressions, this is actually a very well-behaved thing to study, and we can actually say a lot about it. So you can just find the essential P dimension of some branch cover as the least D for which there exists a P compression onto a D-dimensional thing. All right. And sort of alongside this, and this is sort of where Benson and Mark and I came in originally, there's this notion of resolvent degree that, again, goes back to, really Schoenhaus, but then Hamilton and then Klein picks it up and makes a big deal of it. And then this forms the basis of Hilbert's 13th problem, where you ask, like, what's the minimal D such that you can build a given branch cover using some sort of tower of auxiliary branch covers, right? Or in the language of algebraic functions, like, what's the minimal D where there exists a formula for that algebraic function using only functions of D or fewer variables? Formula corresponds to tower of branch covers in the geometric language. Algebraic function, classically, we know it's where Riemann surfaces and more generally branch covers come from. So that's the kind of thing that we're playing off. And you can sort of see this related to essential dimension as saying that, essential dimension measures the complexity of individual blocks. Here we're saying if you allow yourself to stick together some finite number of blocks of, complexity no more than D, how far can you get? And that's sort of what resolvent degree is asking. All right. Any questions on these definitions at all? All right. So we can restate the theorem. We can say that, this is the theorem I sort of stated at the beginning. If you have a complex abelian variety, then for all but finite landing primes, its essential P dimension, or the essential P dimension of its P isogeny cover is the dimension of the abelian variety, is max, right? If you look back at the definitions, like all these things, like the essential dimension is no bigger than the dimension of X itself, right? The identity map is a trivial compression, it's a trivial P compression. The identity tower is a trivial solution, sort of a tautological solution. So you have, these upper bounds just coming from the dimension of X, and the question is, what about the lower bounds, right? And for essential P dimension, in this case, the lower bound is the upper bound. So we have a sharp computation. All right. And just to kind of remark, like, these P isogeny covers are abelian covers. P roots are one variable functions. Radicals more generally are one variable functions. So you can the resolvent degree of these covers is 1. So this is just an example of how wide the gap between essential dimension or essential P dimension and resolvent degree can be. Arbitrarily big. And another kind of glaring thing to mention, and this is just the thing that is, to borrow a phrase I learned from Craig a few years back, this problem is continually harshing my mellow. For all we know, resolvent degree, though it's been studied by, famous mathematicians, and there's been a lot written on it, it could just be that we, the mathematical community, are really missing something fundamental, and this is actually a really complicated way of computing the constant function 1, right? We don't know. We don't have any methods at present for proving lower bounds, non-trivial lower bounds on resolvent degree. Hilbert's 13th problem, you can capture the essence of it by saying, show that resolvent degree is at least, is greater than 1. It's non-trivial for any algebraic function, right? We don't have a single example. We have some conjectures. Hilbert conjectured that the general degree 6 polynomial has resolvent degree 2. His 13th problem is that the general degree 7 has resolvent degree 3. 2 and 3 come from work of Hamilton and Klein, writing down explicit formulas. And Hilbert was in some sense saying, like, Hamilton got these formulas. 50 years later, Klein worked super hard with the full range of mathematics available to him at the time and got the same numerics, different formulas, but no simpler. Maybe the reason is that these are, actually sharp. And those conjectures are still wide open today. All right. Yeah. Great. So that's sort of the problems statement of the talk, at the theorems, and I'll sort of work my way through the conjectures and mistakes and ideas as well. Any questions on that? Great. All right. So I don't know if this is conjectures, mistakes, and ideas. These are all like deep in this sort of structure of the mathematical mushroom. So I'm never super clear on exactly where one ends and where one begins. You sort of have to tease it out. I'll phrase this as an idea, and it's kind of a marvelous idea. Is especially in topology seminar, it's common that people might have known, will have heard about Arnold's contribution to the cohomology of braid groups and launching the whole upwelling of studying kind of hyperplane arrangements, which grows out of a couple of papers that he wrote in 1968 and the early 70s. If you go back and look at those papers, this is the title of the first one. It's called On Some Topological Invariants of Algebraic Functions. And Benson and I sort of got into this again by reading this mushroom paper of Arnold from the end of his career, but then going back and realizing that the papers that we knew about homological stability for braid groups were actually intended to be something else. And Arnold was really sort of trying to find topological methods to touch Hilbert's 13th problem. And his basic idea in these papers, and it's kind of a marvelous one, is that there is a dictionary between vector bundles on the one hand and algebraic functions on the other. And he sort of proceeds to kind of develop this dictionary and sort of launch this dictionary in this series of papers. And the first thing you'd sort of note is that, okay, well, the structure group for a vector bundle, GLN, that corresponds to the braid group in Arnold's telling as a kind of structure group for an algebraic function. And you could say, okay, but that structure group better correspond to a classifying space. And Arnold posits the configuration space of unordered points in the plane as the analog for algebraic functions of the the infinite Grassmannian BGLN. Then he pushes further and says, actually, like Schubert cells are a really important structure, way of accessing the homology and cohomology, the intersection theory on the infinite Grassmannian. And we have a similar, very important structure for configuration space, namely the Fox-Norworth cell structure. And then he says, okay, and the reason we're introducing these in both cases is that by studying the classifying object, we get a good theory of characteristic classes. And these theories of characteristic classes allow us to detect subtle topological phenomena about the objects in question. Right, so he's sort of building up this idea of characteristic classes. And what his goal is, and he's quite explicit about this, especially in the sequel to the paper I showed, is that he wants to use characteristic classes to solve resolvent problems. And in particular, he wanted to use characteristic classes to try to find a topological witness to RD, to resolvent degree being bigger than 1. All right. And when you state this idea, one, as a topologist, I'm like, that's a cool idea. I hadn't sort of heard of that before, about 5 or 6 years ago. But it's in keeping, characteristic classes are obstructions to, sort of trivializing your bundle in various ways. And you sort of stare at this and you realize there are sort of 2 fundamental challenges to kind of making this idea work, to be able to use characteristic classes to solve resolving problems. And the first one is that, we kind of, if you state it purely algebraically, for most people and in most contexts, it's sort of obvious that you get to use all of arithmetic to rewrite your formulas. In particular, you're allowed to divide by anything that's not 0, right? And if you phrase that geometrically, that says that maybe there's some bad locus where you've divided by some term that vanishes on some subspace of the base of your branch cover, but you'll throw it out and you'll pass to some dense risky open, and then you'll be able to write your formula there. It's a very classical thing. You can go back to work of Lagrange and Abel and Bring in the late 18th, early 19th century, and see that this is right in play. And so if you're gonna have a good theory of characteristic classes that's going to obstruct solutions, it needs to survive restrictions as risky opens, right? And this is something which I'll still say, like, the range of topological invariants that we have access to that survive restriction to arbitrary as risky opens is not very rich as far as this problem is concerned, right? So this is maybe a challenge to topologists of take birational geometry seriously. It's a very rich playground and we need a lot more tools, right? So I'll advertise that. And this this problem, this challenge, for all the flavors of resolvent problems that I'm talking about today, ED, essential dimension at P, and RD, this obstruction is there. And another one, and this is particularly thorny for resolvent degree, is that you need some way to guarantee that, you know, your classes survive pullback along branch covers, right? There, you're allowed to pass to some auxiliary branch cover or some tower of them, and maybe after pulling back along that tower, then you can simplify. And there are very, very few methods that can guarantee that classes will survive pullback along that, or even find invariants that can do that. And we'll also just sort of say, just to kind of give context, in the literature, there are techniques that solve one of these problems at a time, right? I'm not aware of any techniques that can solve both of them simultaneously, and that's really the interaction between, on the one hand, the birationality of this problem, and on the other hand, the need to grapple with auxiliary covers. Those two together seem to be where all the challenges. All right. And so you could ask, okay, can characteristic classes detect resolvent degree greater than 1? This is like sort of Arnold's dream. And 50 years later, you can say definitively no. And that was, I felt sad when I realized that. And one really powerful explanation for it comes down to the norm residue isomorphism theorem, or this theorem of Bloch-Kato. And you can rephrase that as saying that every mod P Galois cohomology class dies after pulling it back along some p root cover, right? Because radicals are one variable functions. That means that these invariants can't detect anything of RD greater than 1. And you can say this in geometry just by saying, like, if you hand me a mod P class on any complex variety, after restricting to some Zariski open, and then adjoining a cyclic P cover, the class dies when I pull back along that, right? So it's some sort of like strong anti-transfer theorem is, I guess, how I would think of it, right? All right, in like mod P cohomology. So you can sort of look at that and you can say, okay, that's bad, but maybe we haven't totally given up the game, because you know, you look at our friends in algebraic geometry, and most of them who are studying birational geometry aren't restricting to arbitrary Zariski opens and working with function fields. They're working with like blowups and smooth projective models, and you know, maybe there's something to be gained by like hanging on to your variety. And I'll call this work in progress, but you can show pretty convincingly that that actually does not give a way out of it. And then in hindsight, maybe you could see, well, this is probably something like Bloch-Kato for Borel-Moore homology rather than, or compactly supported homology rather than Galois homology. But you can actually get quite explicit information on where the branching of this p-power cover lies and how that trivializes a given characteristic class or given cohomology class. So Arnold's kind of original vision here is just not going to work. And at this stage in this project, you know, that Benson and Mark and I have been working on for about 5 or 6 years, I can basically say that none of the way that we know how to hear any of Arnold's ideas on this, we can prove that none of those ideas can work. And so then we have to find, you know, new ideas, and that's sort of where we're at. All right, but you could ask, like, how about, you know, essential dimension, or how about essential p dimension? And here the challenge is sort of much more controlled. Classes need to survive restrictions to Zariski opens, and if we're throwing out, if we're in essential p dimension, and we're saying our accessory branch covers have to have degree prime to p, that puts us in the case where we have transfer in mod P cohomology. So transfer is sort of like the one tool that we as topologists have for showing that a cohomology class, you know, survives upstairs in some cover, and we can sort of actually kind of, you know, really focus on the first problem. All right, so the kind of main topological theorem that kind of makes this work, is, you know, I think of this topological theorem, is if you have me a smooth complex projective variety and satisfying some arithmetic condition, and you hand me any Zariski open, then I can ask, like, how big is the image, or how much of the cohomology survives restriction to that Zariski open? And here I want to say the mod P cohomology. And we put a lower bound saying that the dimension of the image is at least as big as the dimension of the space of holomorphic forms of that dimension on the variety, subject to some conditions. Right, so in particular, you have like a say you have like a genus G curve and I equals 1, then you can show that in mod P cohomology, you'll get at least a G-dimensional restriction in H1, right? Okay. And then that's basically how you prove the corollary, because the cohomology of the abelian variety is an exterior algebra on its H1. So if you know that the H1 restricts on any Zariski open to something of full rank, then that shows you that a top form or a class in degree equal to the dimension of the abelian variety survives, and that's sort of where we get our witness here. So okay, this is sort of somehow like the meat of the talk. Like, how do we prove this? This is like the kind of the new thing. And if you stare at this, you see that the statement with rational coefficients, this is an exercise in classical Hodge theory, right? You can sort of show one, we know from Hodge theory that on a smooth proper thing, the holomorphic I forms inject into cohomology, and then you can show essentially using logarithmic forms that not only do those forms all restrict to be non-zero on a Zariski open, but they stay non-zero in cohomology. There's no co-boundary that shows up, right? And this is sort of one of the things that's really powerful about forms as a witness for like ordinary cohomology is like, an ordinary cohomology class and singular cohomology, like God knows where it lives. It can kind of wiggle all over the place. And you have a lot of challenge showing that it stays non-zero if you try to squeeze it into some subspace. But a form, form's local. And so you really can have some sort of fine control over cohomology classes by representing them by differential forms. And that allows you to get a nice statement in rational cohomology. And so our trick or our kind of, problem is, well, how do we leverage that to get a statement about mod P cohomology? With that preamble, it shouldn't be surprising, sort of what sort of motivated us, is that you need some other form of Hodge theory that's going to allow you to make the Hodge theoretic arguments for mod P coefficients. And it's really the kind of the breakthroughs the last, I guess, 8 years now, 5 to 10 years, coming out of work of Schulze and Bott and Morrow and others on really rebuilding chaotic Hodge theory that allowed us to kind of get this theorem. And I'll say that in hindsight, you can see a precursor of this theorem with a lot more restrictions on the variety in work of Bloch and Hainaut from the late 90s using the best available chaotic Hodge theory at the time. Sort of this theorem compared to that theorem really shows the power of the prismatic methods. Right? So I guess it's sort of possible that people in this seminar have heard about prismatic cohomology because of all the breakthroughs going on in computations of algebraic K theory and other things. This is sort of another thing that you can do with prismatic cohomology that you couldn't do previously. This is how it happened. All right. Great. So I'm about to launch into the technical part of the thing where I sort of try to give a kind of quick but technical explanation of what prismatic methods are, what the setup is, and then how we use that in this context. Are there any questions or anything before I kind of dive into the last 15 minutes of the talk where I sort of, give some sketch of a proof? Great. Okay, so what's a prism? What's prismatic methods? I'm not going to define the general story. I'm just going to basically tell you the piece of it that's most relevant for what we're doing. And then if that interests you, A, you can go read the paper, and B, you can use that as a way of sort of figuring out what the general story is. I always like to sort of start with an example, get my hands on that, and then try to anchor some general theory by reference to the example. So here QP is the p-adic numbers, and we're looking at some finite extension of that. And I'm going to assume that it's unramified at P just for simplicity. And if you don't know what that means, you can just ignore it entirely. It's an arithmetic condition. And you can think of these fields as some sort of like arithmetic, kind of weird cousin of a Laurent series field, right? That's an analogy that you can actually get. It's an old analogy. You can get a lot of hay out of it. And in particular, you can have these distinguished elements called uniformizers, which function for these fields K, kind of like the choice of coordinate element functions in a Laurent series field, right? Sort of gives you a way of writing all other elements in the field as convergent power series relative to the norm. All right. And now I'm going to assume that I have a variety over K, which I call X. And I'm going to assume it has good reduction, which again means that, maybe after clearing denominators in the polynomials that define my variety, I get some nice variety or some scheme over the ring of integers in this field. And if I reduce that polynomial mod P, then it stays smooth, right? That's sort of the basic idea of good reduction. All right. And then, associated with this kind of setup, this is where you start getting into prisms. You have this notion of both the residue field of your field K. That will be some finite extension of FP. And given such a thing, you have this nice ring called its ring of bit vectors, which somehow sort of spreads that ring, deforms it kind of infinitesimally into characteristic 0. And so that's what our W is. And this idea of a prism is that you're going to build a kind of power series ring over W, and then map it back into the ring of integers. And you do that in a way that's compatible with the kind of Frobenius endomorphism that you built on this power series ring. And somehow that kind of information seems to capture an awful lot of geometry and arithmetic, right? That somehow like the kind of metaphor of prism is that this kind of, you should think of this as giving you some device for splitting the beams in your white light and sort of picking out all the separate colors. And if you've seen a talk of Bhargav Bhatt, he'll actually put up the Pink Floyd cover to sort of make that illustration, right? That's sort of the idea. Somehow this kind of allows you to spread apart and see really finely all the arithmetic data that might be bound up in some hard to access way just in your variety X. All right. So given this kind of setup, Bhatt and Schulze introduced a theorem or a theory called prismatic cohomology. And they did it in the language of sort of p-adic formal schemes. You'll sort of get such a gadget from any algebraic scheme. And if you're given one of these things, well, it's a cohomology theory. So first off, you get some functorial complex in a drive category, which you should think of as like the prismatic cochains, basically. And it has some very nice properties. So if your variety is proper, and it's not only should you think of it as prismatic cochains, but somehow you should think of this as some p-adic analog of the complex of Drum forms. That's really sort of how you want to think about it. And the sort of first property here is that if X is proper, this is a perfect complex, and that's sort of like the first theorem in Hodge theory that says if you have a compact Kähler manifold, then the harmonic forms are finite dimensional, or the cohomology of the Hodge form of the Hodge complex is finite dimensional, right? So that's sort of what perfect complex is. And then what's sort of magical about this, to me certainly, but it's sort of where it gets a lot of series power, is this prismatic cohomology captures and allows you to recover a lot of previously distinct flavors of cohomology that you would attach to your variety. So if X is proper, or just in general, you'll get a comparison map from a tall cohomology of your field over, the generic fiber of your scheme to the prismatic cohomology, right? So the prismatic cohomology somehow knows about the Étale cohomology of the characteristic 0 gadget. It has a Frobenius operator on it, and that Frobenius operator is essentially an isogeny. It's sort of multiplication by a power of u. So you sort of have some relationship where you can really pick up via the module structure this Frobenius. And then if you twist it by Frobenius and you mod out by u, then you'll get the Drum cohomology of special fiber, right? So this sort of gives you some gadget for moving from, say, tall cohomology, or like singular cohomology, if you wish, in characteristic 0, to de Rham cohomology in positive characteristic. All right. And again, they built in a very user-friendly fashion. So your best introduction to this is Bott and Schulze, their 2022 Annals paper, and actually sort of state the main theorem in the introduction of, we produce a cohomology theory with these properties, and in the just sort of sit down and compute approach to learning new things, like you really can kind of take that and start playing with it in examples, and getting a lot of mileage out of it. All right, so that's our kind of package. We're going to use this tool to kind of prove this theorem, that the restriction of the mod P cohomology of a complex variety to any Zariski open is at least as big as the number of holomorphic forms in that dimension. All right, so how do we do that? So, well, we pick some Zariski open. This is going to be, we're going to prove by contradiction. We're going to say, give me any Zariski open. Suppose that the restriction is 0. I'm going to, for the purpose of this talk, I'll just say, suppose the restriction vanished, and then we can sort of, if people are interested, you can sort of see how to modify this to get the full lower bound. But for simplicity, I'll just say, suppose the restriction vanished, right? And so what we want to show is that this thing I'm calling J, this restriction in mod P cohomology, this is non-zero. All right. So suppose it's 0. And we have to do a bit of massaging to kind of get ourselves into the context where we can apply prismatic cohomology theory. But you can just sort of think this as like shrink everything a little bit more. And you'll be able to show just from the sort of setup of the theory that if our first J equals 0, then this second J, which I'm just going to abuse notation and call the same thing, then that also equals 0. Sorry, that should say equals 0 on that line. Sorry about that. And if you grant that assumption, so we're going to derive our contradiction from, then the second property of prismatic cohomology combined with that assumption says that actually the image in the prismatic cohomology, like here I'm looking at a tall cohomology, but the image in the prismatic cohomology has to be 0 mod U torsion, right? We said, I'll just flip back a little bit, that this is a sort of isomorphism once you invert U when X is proper. And you can sort of use that to show that the image has to be pure U torsion. Great. Okay, so now we're gonna move to studying this analogous image in prismatic cohomology. I'll call that J sub prism. And the lemma is that under the given conditions on X, and P, and here P is at least the degree of cohomology plus 2. Then we're going to show that this image has no U torsion. And for this, we're going to use the Frobenius property. So the first thing is that because X is proper, this image is finally generated as a module over the algebraic closure of K, this power series ring. And then if we, property 3 said that we can completely control what Frobenius looks like in degree I cohomology, and it's just multiplication by the U to the I. So once we have finite generation, we say essentially like, assume that there was some torsion, and then because it's finally generated, there's some least exponent such that that exponent kills everything in the torsion. And then we're going to sort of show using Frobenius that actually that exponent has to be 1, right? And so that's sort of how we derive the contradictions. That's sort of the sum algebra. And there's a bit of subtlety with like derived completions, but essentially that's the idea. You sort of you use the finite generateness in a strong way, plus Frobenius to push the torsion into a contradiction. So there couldn't have been it. All right. So now we've gone, because that lemma, from showing that we can just assume that this image in prismatic cohomology is not 0 mod torsion, but is actually 0 on the nose. All right. And so now we're going to use property 4 to say that if it's 0, then that would imply that the image in de Rham cohomology would be 0. But now we're in characteristic P, so we're in the special fiber. And again, like in the classical argument, with rational coefficients, the magic that allowed you to control when a cohomology class survived as Zariski open was you said, well, we have Hodge theory, so we can represent that cohomology class by a local object, namely a differential form, and then differential forms just manifestly don't restrict to zero, and that's our witness. And it's this step right here where we've now used the prismatic cohomology to produce from a singular character, singular cohomology class in characteristic zero, something local, right? A de Rham form, okay, in positive characteristic that we then want to show survives. And now we're sort of very close to this. And we sort of have to finish the job by showing that enough of Hodge theory in characteristic zero carries over in a certain sense into the positive characteristic sense to get it done. And that's essentially classical. So I'll walk through that now. So we're now reduced to showing that this image in de Rham cohomology is zero, is non-zero. And for this, we're going to sort of use this classical trick. So if I have a scheme over some positive characteristic field K, then I can sort of form the Frobenius twist of that scheme. I sort of pull it back along Frobenius. Same underlying space, but different ring of functions, different scheme structure. The analog, or I think of it as the analog of the Hodge de Rham spectral sequence in positive characteristic, is this conjugate spectral sequence that starts from the cohomology of Y with coefficients in the de Rham cohomology naively thought of, and then ends in the sort of the de Rham hypercohomology in the classical language, but the non-naive thing that you'd actually mean by de Rham cohomology there. And Cartier, observed that actually you have an isomorphism where the terms showing up in this E1 page of the spectral sequence can actually just be rewritten as the cohomology of the J forms after the Frobenius twist. So you sort of get to drop the cohomology on the coefficients at the expense of passing this Frobenius twist. And if you use affine, then you can show that the only term in the spectral sequence which contributes to this image that we're concerned about is just the restriction of I forms to I forms, right? These are coherent sheaves, so the things affine, they have no higher cohomology. And then Deligny-Luzzi proved that under the assumptions we're working with on X, if X is smooth and proper and with good reduction, then the spectral sequence actually degenerates at the E1 page in the exact same way that the Hodge de Rham spectral sequence degenerates at the E2 page for a proper complex variety. And so now we're done, because we just have to check this thing is non-vanishing on E2 on this term to see it. So that sort of says, okay, by all that the above, the thing that we're considering just is restriction of I forms on the special fiber, maybe after Frobenius twisting, to restriction of I forms on this Zariski open. The sheaf of I forms is, global sections is a lower semi-continuous. So the dimension of the space of global sections is lower semi-continuous than families, right? So the number of I forms in characteristic zero, that's the generic fiber, there are at least as many I forms in positive characteristic as there are in characteristic zero. And so this is how we sort of go from the characteristic zero lower bound to the whole thing. All right, so that gives a contradiction. Great. Are there any questions on that proof at the level of detail I gave it, or any place where people want any additional detail, or any comments or questions, criticisms at all? All right. Hearing none, and I think I'm sort of really nearing time. Yeah, I should have said that. All right. So I told a story, and the story was, we had some problems. We can prove a theorem. The theorem answers a recent conjecture. It uses some methods, but these problems kind of come to us in the context of this much older set of problems about like how hard is it to solve a polynomial, or in this language, like is resolvent to be greater than one. And I sort of close with this picture, which is sort of, I think, is captured where we've been in this collaboration for about a year. If anybody recognizes this, this is the reference to the story of the monkey god when Buddhism was brought to China, sort of sitting in the Buddha's hand. I'm happy to sort of explain in more detail sort of how to think about it. But I'd say the summary is we've worked really, really hard for a long time. And as far as we can tell, or it's totally possible that we haven't made any fundamental progress on the core problem, as this picture sort of would tell you. So I'll stop there and open for questions and say thank you again for your attention for the last 15 minutes.